recording.
Howdy. My name is Maya Tensei. This is group one, and we're working on a flywheel piston system. These are my other two group members.
Howdy, I'm Cyrus.
Hi, I'm Janelle.
Yeah, and we're group one. We're currently recording our video, so we'll put our YouTube video link in that location once we're finished recording, and that team folder link is should be up to date, and it is shared with everyone, and so anyone can view the link without having to log into Google.
Yep. All right, so on to our project description. So we are going to do a flywheel system, which can also be seen as a slider crank system. So basically what we are doing, we have a motor and then we have a flywheel. The motor is what's going to actually actuate our flywheel, moving a pin that's connected to another pin, which is connected then to our piston. So we are going to have a torque being applied from the flywheel, which will then be moving the mass back and forth. So what we will see is rotational motion being turned into linear motion by the system. Um, so the input to our system will be velocity, which will be measured um, from our flywheel, and then our output will be measured as position. So doing this from our position, what we will do is calculate the period of the movement. So we'll be able to find out how often it's completing a full period. This will be useful because from our experimental data, we will be able to compare that to our simulated data to see how accurate the data will be. So the main goal of this system is basically to understand how the rotational motion is turned into linear motion, and that's the project description. And then onto the plan of execution. So first up, we have the mechanical part, which will the mechanical part. The tasks are to use SolidWorks or some sort of CAD to design the flywheel system. Um, And then from that design, we will be 3D printing it to so that we were able to prototype it, create our final um, flywheel piston to actually be able to test it. And then we'll gather data from it using sensors and the model that we had designed, 3D printed, and assembled to then eventually compare with our simulated data. And then onto the electrical and computer plan of
Yeah,
execution.
so we'll have the motor driving the flywheel, of course, and we'll need a way to measure its rotational velocity. I have a Arduino like microcontroller that we can use for this project, and I found several sensors that we could attach to it to measure like the rotational velocity. And then we could also use another sensor for the displacement of the mass at the end so that we can count how many times that mass like gets close and then it'll leave and then come back, right? So being close to the sensor, leaving and then coming back, that'll be one like cycle, and we'll count the speed of those cycles. And just like it's the mass's relationship and its position from left to right according to the rotation of the flywheel. And then also I'm gonna have to code the microcontroller just to be able to control the speed of the motor so that there's a varied voltage heading like a basically a PWM signal being sent to the motor to control its speed, in addition to making sure that we are getting recordings from the input velocity and the output displacement.
Moving on to simulations. Simulations will involve modeling systems and simulating that we will derive equations from the motion of rotational and mass assist. Okay. We will also build a Simulink using estimated parameters, and then we will use those parameters in order to oh, sorry, collaborate the model with the experimental data.
And so, in terms of distribution of work, I will be the primary person taking care of like the electronics, the controller, the sensors, and being able to send the variable speed to the motor, getting all the parts, and setting that side of the circuit up.
I will derive the systems equations of the free body diagrams, and then I will also build and collaborate the Simulink model. I will also analyze the simulation versus experimental results.
And then I'll be responsible for the mechanical part of the project. So that deals with creating the CAD model, 3D printing the CAD model, and assembling it to get our physical flywheel piston. And then from there, I'll take measurements from the model, from the physical model, to get our experimental data. And that is our distribution of the workload. And then here is the timeline for the project that we have. Um, so as you can see, so starting on task 3, we have the mechanical model, which is what I'll be working on. So we want the first 3D CAD design to be finished by the 13th. And then on that day, I should be able to start prototyping, which will like that includes 3D printing, putting it together, making sure the prototype actually works to become our final product. And in this time span, we will start to finish making changes so that we can start collecting data. So our prototype should be completely finished by the 19th. And then by the 24th, our final model it'll have no more changes. We'll have our position and angular velocity measurements. And then that'll be it for the mechanical model timeline.
Yeah, and for electrical components, generally, it's going to be like a first week up until around the 13th, the 14th mainly, to figure out what components I'll need, like nail down what specific sensors I'll be using, and give them time to arrive here in College Station, at my apartment mainly. And so that's on the 14th, and then after that, it'll generally be hopefully working with Cyrus on what the physical model looks like in order to put them into place, have them finalize their location and their placement so that there's a place for the marking controller to go and just for our prototype to generally, on its way to completion. And then that last week, uh, up until either the 22nd or even afterwards, because again, Cyrus is also still finalizing his model at that time. We'll be able to work together to record our final bits of data for our and like test out any problems of if our data is somehow miraculously incredibly wrong, like figure out what's happening. Um, and that should be hopefully done around the 22nd or I remember Cyrus's is the 23rd. So
And then for the Simulink model, I would derive the equations by the 13th, make the model by the 18th, and then compare simulated to experimental model by the 20th.
And then that'll be it for our timeline and then our expected outcomes.
The expected outcomes are functional electromechanical systems demonstrating oscillating motion. Simulink model is accurately predicting system behavior. Comparison between real and simulated data with a less than 10% error. Clear understanding of rotational and translational energy dynamics.
And with that, we hope to also have a better understanding of how the rotational system converts energy to a linear system. And with the help of the Simulink model, we should be able to, I guess, better characterize the physical model that we have in a simulated version that accounts for our dampening, the torque, the mass. So yep, that's our expected outcomes, and that is a project proposal. Thank you for your time.
thank you. Bye bye.
Bye bye.